Okay, I think we better get started. So welcome everyone to the Supernova Rubin Research Bytes session. So we have a pretty fast schedule here. I'm Clare Saunders and I'm going to be sharing with Chien-Hsiu Lee. So we have four quick talks, and then we're going to have all the question and answers at the end. So you can put questions in the chat here, or you can put them in the Slack channel, and Chien-Hsiu is going to be moderating that. Okay, so as with all of the other talks, please remember you have agreed to abide by the code of conduct. So that means that Rubin adheres to the principles of kindness, trust, respect, diversity, and inclusion in order to provide a learning environment that produces rigor and excellence. Any discriminatory behavior will not be tolerated. And you've all agreed that if you witness any bullying, harassment, or aggression, you'll follow the reporting instructions in the code of conduct. So just something to remember again. Another thing, so as I said a few minutes ago, this talk is being recorded. The videos should be posted by tomorrow, and you can give, in the Slack, you can give questions that you like a thumbs up, and you're also free to show your appreciation with applause through the Zoom app. So with that, I think we can go ahead and get started. So the first talk is going to be by Franklin Crenshaw, and John, you can go ahead and start. So, John, I think you're muted.
Sorry about that. So I'd like to talk about some work I've been doing with Andy Connolly at UW and Tomas Budivari at Johns Hopkins to reconstruct spectra from photometry. So the idea is that if you have a set of photometry that represents some underlying class of objects, then you can treat this photometry at different redshifts as an ensemble of observations of the same underlying rest frame spectrum at with a bunch of different blue shifted filters. So this equation shows that you can calculate synthetic photometry, assuming that we know the spectrum, given the filter curves, and you can see that we've blue shifted the filters here. So what we want to do is minimize the square differences of the measured photometry with the synthetic photometry. And so what we do is we treat the spectrum as some perturbation on some prior, so that can be some prior knowledge, or you can set that to 0 if you just want to learn it from scratch. We also include bias terms. And so we have these regularization terms here. And so we're going to do this minimization to estimate these spectra. Next slide. So we applied this method to Galaxy SEDs for photo Z estimation. So on the right there, you can see Galaxy photometry plotted in orange. We got these from a variety of different photometric surveys, and we split them into 8 different groups based on their rest frame colors. And we applied the algorithm to learn the templates, the spectrum, which are in black. So you can see that we recovered stuff from red ellipticals up to blue starburst, and we have some high resolution features like these emission lines that are plotted, that are marked in gray. So we tested them using BPZ to get photo Zs, and we found that it improved the photo Z results compared to the standard set of templates that come with BPZ. So I linked a paper down here in the archive that you can see more of these results. Next slide. So now we want to apply this to supernova light curves. So here on the left, you can see that I started with just a SALT2 model for a type 1a supernova. We simulated photometry. We sliced the photometry into different time bins. And for each time bin, we just reconstructed like we did the Galaxy spectra. So on the right, you can see the reconstructed version. It just looks like a noisy version of the original. So our goal is to apply this to the plastic photometry to get a more realistic test, and hopefully see if we can improve distance estimates for 1A supernovae using these photometrically derived light curves. And then eventually we would like to apply this method to other classes of supernovae and other variables and transients with LSST. So if you have any imagined use cases, we'd love to hear it. Thanks.
Okay, thank you, John. Moving on to Alex.
Hi, everyone. My name is Alex Gagliano, and I've been working with Gautam Narayan on constructing a database of classified supernovae and the properties of their host galaxies. I've been using two main methods to associate supernovae with a host galaxy. The first is the directional light radius, or DLR, in which the angular separation to each candidate host galaxy is normalized by the radius of that galaxy in the direction of the supernova. This has the advantage of allowing us to directly compare large hosts and small hosts, but it can fail when crowded fields make it difficult to disentangle the light profiles of multiple sources. To resolve this problem, I've developed a new host galaxy association method called gradient ascent. The algorithm works by calculating the two-dimensional gradient across a postage stamp and following the gradient field from the supernova to a local maximum. Gradient ascent is 25% more accurate at low Z and significantly more complete at high Z than the DLR method. Next slide, please. We can use this supernova host galaxy database to begin classifying supernova events. I've trained a random forest algorithm on 7,000 events to distinguish core collapse and type 1a supernovae. On the left, I show a confusion matrix describing the fraction of events correctly and incorrectly classified by the model. We can distinguish these events with around 70% accuracy before we've gotten any information from the explosion itself. The variable importance plot on the right shows the most significant features used by our model. We can group these features into three categories. Angular offset, which supports previous findings that 1As and core collapse events occur at different separations from their host centers. Galaxy color, which is indicative of metallicity and global star formation rate, and morphological features that characterize the light profiles of our galaxies. All of this information will be provided by LSST or can be calculated as soon as an event is confirmed. Next slide, please. The catalog of host galaxies I've created, called GHOST, can be found at ghost.ncsa.illinois.edu. This website features postage stamps for all 16,000 host galaxies in the database and provides detailed information about each event. A search bar allows users to query the database for the host galaxy, supernova, or supernova class of their choice. In the future, we'll switch from a random forest to a neural net model to classify on galaxy images directly, as they contain richer color and morphological information than the single values that we've been using from pan-stars. We'll then integrate this software into a photometric classifier for robust early time classification in upcoming surveys. Thanks.
Okay, thank you, Alex. Next up is Daniel.
Hi, everyone. My name is Daniel Perrefort. I'm a graduate student based at the University of Pittsburgh. One of the things that I'm interested in studying is the properties of peculiar type 1a supernova. So LSST provides this really great opportunity because we're over the next 10 years of its life, we're going to be observing somewhere in the ballpark of 1 million supernovae. And this is great because a lot of the peculiar objects that we study as supernova scientists only have a small handful of objects that we've actually been able to observe. So this will help flesh out our sample sizes and help us understand the properties of those objects. Unfortunately, LSST is a bit of a double-edged sword because we're going to have way more photometrically observed objects than we're going to be able to follow up spectroscopically. So the solution to this, as I'm sure most of the supernova people are aware, is the development of photometric classifiers. So if we could hop to the next slide. So there's been a lot of different approaches to this problem. Machine learning has been a popular solution. One of the approaches that I've been working on is actually a template-driven approach targeted at finding a specific type of peculiar type 1a supernova. 1991 BG-like objects are objects that are dimmer than the normal supernova population. They also have slightly different morphologies to the evolution of their light curves, and they're redder and decline faster in their overall brightness. And so one of the ways that you can identify these objects is essentially by performing 4 light curve fits that I'm showing in the right side of this panel. You take 2 models, one that represents a normal type 1a supernova and one that represents a type 1a supernova that you're interested in. And then you separately fit both models in the rest frame blue and the rest frame red. So this gives you an indication of how well each model performs in the blue band passes and in the red band passes of that particular object. Okay, move to the next slide, please. The information that this gives you allows you to compare the chi-squared values in the blue and the red. So you can ask the question, is this object in the blue more like a normal or more like a 91BG object? Same question can be asked in the red, based on its chi-squared values, is it more normal or more 91BG? And when you plot this out in a simple parameter space where you plot out the difference in the red versus the difference in the blue, objects that are more like a 91BG pop up in the right-hand corner. Objects that are more like a normal pop up in the bottom left. Normal objects here from CSP are shown in purple. 91BG objects from CSP are shown in red. And what this allows you to do is isolate a specific type of object that you're interested in. So then you can both schedule spectroscopic follow-up at late times, which is really good for constraining current supernova models, but then also select targets and observe their properties as a collective.
Okay, thank you, Daniel. And the last talk will be from Francisco.
Your microphone, Francisco.
Sorry. Sorry, my name is Francisco Forster. I'm speaking on behalf of the ALeRCE broker, a Chien-Hsiu broker which aims to provide a rapid and robust classification of variable events. Today we'll show the results of one of the two classifiers used by ALeRCE, the stamp classifier. If you want to learn about the Lightcurve classifier, see the parallel talk by Paula Sanchez-Saez in section H. Okay, so this first slide, I show you the evolution of real Bose classifiers. Since the pioneering work of Beatty et al. 2007, which used random forest and other more classical methods to separate real and Bose in automatic fashion, in 2016 we introduced convolutional neural networks to this problem in Cabrera-Vives et al. 2016. Now we also use convolutional neural network, but we go beyond the real Bose classification using an expanded taxonomy in Carrasco-Davis et al. 2020. This new classifier is able to classify alerts into 5 classes using only the first stamp triplet with reasonable accuracy, as shown by the confusion matrix on the right. Next slide, please. In order to take advantage of this classifier, we have developed a web interface called the Supernova Hunter. In this interface, users can explore the best candidates in real time, providing labels for possible supernova or Bose. Through this process, we have been able to significantly enlarge the sample of Bose candidates in our training set, obtaining more than 30,000 visual classifications. Next slide, please. Finally, I show some results allowed by this new classifier. On the top and bottom left panels, you can see 2 nearby supernova, which were detected by CDF and reported by ALeRCE using only one detection. After the first detection by CDF and a report by ALeRCE only a few hours later, Spectra could be taken significantly before the second CDF detection, which was many days later in these 2 cases. In the top and middle panel, we show some statistics. On the top middle panel, we show the cumulative distribution of times between report and first detection for both AMPEL and ALeRCE. And here we don't count repeated candidates. You can see that ALeRCE is dominated the 1-day timescale reports, which is critical for flash spectroscopy. On the bottom middle panel, we show the distribution of classified objects, with almost 450 supernova spectroscopically classified. Finally, to summarize, we have reported more than 3,000 supernova to TNS, about 450 of them spectroscopically classified. ALeRCE is contributing most candidates on the 1-day timescale, which is critical for flash spectroscopy. And the price of doing this is, the one stamp classification is about 20% contamination. But we expect that one stamp classification will be very important for fast classification and follow-up under LSST's observing study. Thank you.
Okay, thank you, Francisco. Okay, so now we'll move to the question period.
I haven't seen any questions. If you have questions, please put it in the Zoom chat or in the Slack channel. Oh, so I got one from Eric Bam. So question for Francisco. What sets the delay between the CDF detection and the other, say, TNS report?
Yeah. So the classification is actually only less than 1 second, but we visually inspect the candidates because if we're doing one stamp classification, it's very risky to report directly to TNS. So usually it's a few hours, and now that we have a veto system, it could be half a day maybe. So we're trying to we're really aiming for purity now. But if you go to Supernova Hunter, you can check the candidates yourself, and they will be there in real time.
All right. I don't see any question for now, but then now it's question for John. So for John, have you thought about using real data like the Twiki trans facility to do the classification?
That's definitely the ultimate goal. We used real data for the Galaxies, but right now as we're just starting the supernova analysis, we're starting with synthetic stuff so it's well behaved and we can understand everything from front to back. And then hopefully we'll apply it to real data.
Sounds good. Yeah, it usually takes quite a lot of effort to apply from simulated data then to the real data. So I can imagine that's quite some work there. So I have another question from Daniel to John. So for John, have you applied the reconstruction process with other supernova models or templates? And if so, how does doing that provide the information on which models may perform better?
So do you mean other like models for 1A supernovae or other like classes of supernovae?
I guess my question is targeted at 1A supernovae, but if you can also do other types of supernovae, that would be impressive.
So far we've only used the SALT2 model for the 1As. We haven't progressed extremely far in the supernova analysis yet. But if that's something that you think would be interesting and viable, that's one we can definitely look at.
So I had a question for Alex, which was when, actually I'll just send the host, I'll move to this slide. So when you talk about the what the random forest could do, I think you said this was only with the host information, or that was the host information plus some supernova characteristics?
So this is host galaxy information plus the position of the supernova, but no photometry or spectral information.
So the position of the supernova, like with respect to the radius of the galaxy?
Correct.
Okay.
Yeah, I don't have, oh, so yeah, I see another question from Francisco. So this question is for John. So have you thought about building spectroscopic templates for a given class based on many objects of a given class in Spectra?
So building spectroscopic templates for different classes of objects is the primary ultimate goal of what we're doing. I'm not sure how that directly relates to. I think you're saying if we also have spectra for those objects as well.
Oh, sorry, that was a mistake. Observations.
Sorry, can you say that again?
No, I didn't mean the spectra in the end. It was more observations. That was I misspoke. Yeah.
Oh yeah, and that's definitely our ultimate goal. And definitely a benefit of this method is that you can easily incorporate broadband photometry. You can incorporate narrowbands, all that kind of stuff. You can easily incorporate, and we're trying to derive templates for various classes of objects.
So I don't see any more questions on Zoom or on Slack channel.
Okay, maybe we can stop there then and give people some time to switch to the next session or decide which session they want to go to.
Yeah, that's a good idea. Thank you for joining this session.
Thank you. Bye bye.
Hi, John, just saw your question. We are going to start the second round at 11:15. Okay, we're just going to give people another couple minutes to switch rooms and then we'll get started. I'll just check again before we get started. Can everyone see the slides? Yes, okay. Okay, let's go ahead and get started. Okay, so welcome everyone to the second session of the Rubin Research Bytes. This is the Supernova session. So I'm Clare Saunders and I'm going to be chairing along with Chien-Hsiu. And we have 4 talks today, so we'll go ahead and get started. So as you will have just heard, remember as always to abide by the code of conduct. A quick reminder here of what that constitutes. And also this session is being recorded. The video is going to be available tomorrow. And you can ask questions either in the chat here in the Zoom, or you can ask questions in the Slack channel. If you see a question you like, be sure to give it a thumbs up. And you can also show your appreciation with the applause emoji in Slack or on Zoom. Okay, so we'll go ahead and get started with John. John, you can go ahead.
Hi, I'm John Franklin. I'm going to talk about a project I've been working with Andy Connolly at UW and Tomas Budavari at Johns Hopkins. Our goal is to try to learn spectra and light curves from large samples of galaxies or supernovae or other objects from broadband photometry and redshifts. So the idea is that if you can assemble a set of photometry for many objects of a given class, that we can derive a spectral template representing that class. So this equation up here, you can see that you can calculate synthetic photometry if you know a spectral template, and the response filters of the curves of the response curves of the filters it was measured in. So what we do is we model our template as some prior template plus a perturbation. You can set the prior to 0 if you just want to learn from scratch. Sorry. So we have filters as well, but biases for our filters as well. So you can we want to learn this underlying template by minimizing the squared difference of our synthetic fluxes with the measured fluxes, and we have regularization terms on our perturbation and biases as well. Next slide, please. So we applied this method to galaxy photometry. So we collected photometry from a bunch of different photometric surveys. You can see the photometry plotted on this plot on the right in orange. We split the photometry into 8 different groups from their res frame colors, and then we use our method to reconstruct the templates, which are plotted in black. you can see that we recovered high resolution features like emission lines that are labeled in gray. So we tested these templates by using them to estimate photo-Zs. And we found that it improved the outliers, the bias, and the scatter of the photo-Z results compared to the standard set of templates that are used in BPZ to calculate photo-Zs. And you can get more details of that results from this paper we put out in the archive yesterday. Next slide, please. And so finally, we want to start applying this method to supernova light curves. So on the left here, we have a plot of a salt-2 supernova model that we simulated photometry for. We sliced the photometry into time bends and then reconstructed each time bend, each time slice in the way that we reconstructed the galaxy spectra. And so on the right, you can see the reconstruction. It looks like a noisy version of the true underlying curve. So we want to apply the method to plastic data to have more realistic simulations and see if we can reconstruct spectral templates for 1A supernovae and other types of supernovae as well. So we're hoping that we can use this to improve 1A distance measurements using photometrically derived light curves. And we want to apply this to more generally learn spectral templates for other supernovae and variables observed with ALeRCE. So if you have any imagined use cases, let us know. Thanks.
Okay, thank you, John. Moving on to Alex.
Hi, everyone. My name is Alex Gagliano. I'm a graduate student at the University of Illinois at Urbana-Champaign, and I'm working with Gautam Narayan to construct a database of classified supernovae and the properties of their host galaxies. I've been using two main methods to associate supernovae with a host galaxy. The first is the directional light radius, or DLR, in which the angular separation to each candidate host galaxy is normalized by the radius of that galaxy in the direction of the supernova. This has the advantage of allowing us to directly compare large hosts and small hosts, but it can fail when crowded fields make it difficult to disentangle the light profiles of multiple sources. To resolve this problem, I've developed a new host galaxy association method called gradient ascent. The algorithm works by calculating the two-dimensional gradient across a postage stamp of the field and following the gradient field from the supernova to a local maximum. Gradient ascent is 25% more accurate at low redshift and is significantly more complete at high redshift than the DLR method. Next slide, please. We can use this supernova host galaxy database to begin classifying supernovae. I've trained a random forest algorithm on 7,000 events to distinguish core collapse and type 1As. On the left, I show a confusion matrix describing the fraction of events correctly and incorrectly classified by our model. We can distinguish these events with around 70% accuracy without any event photometry or spectroscopy. The variable importance plot on the right shows the most significant features used by our model. We can group these features into three main categories. Angular offset, which supports previous findings that 1A supernovae and core collapse events occur at different separations from their host centers. Galaxy color, which is indicative of metallicity and global star formation rate. And morphological features of the host galaxy that characterize their light profiles. All of this information will be provided by LSST or can be calculated as soon as an event is confirmed. Next slide, please. The catalog of host galaxies I've created, called GHOST, can be found at ghost.ncsa.illinois.edu. This website features postage stamps for all 16,000 host galaxies in the database and provides detailed information about each event. A search bar also allows users to query the database for the host galaxy, supernova, or supernova class of their choosing. In future, we'll switch from our random forest to a neural net to classify on galaxy images directly, as they contain richer color and morphology information than the single values that we've been using from pan-stars. We'll then integrate this software into a photometric classifier for robust early time classification in upcoming surveys such as LSST. Thanks.
Okay, thank you, Alex. And next will be Daniel.
Hi, everyone. I'm Daniel Perrefort, based at the University of Pittsburgh. And one of the things that I think a lot about are type 1A supernovae. In particular, I study the properties of peculiar type 1A supernova objects. And LSST is going to be really great for this because We're going to be observing on over 10 years an order of 1 million new type 1a supernovae. And so that's going to really help us fill out data sets of peculiar objects, some of which, depending on the object you're interested in, are actually really poorly sampled. And so this is a bit of a double-edged sword, because even though LSST is going to give us all these objects, as we all know, spectroscopic follow-up for LSST is going to be a pretty serious challenge. And so the solution to this is to develop a set of photometric classification tools that allow you to identify the objects that you're interested in. Next slide, please. So there's been a lot of different approaches to this challenge. Machine learning has been a very popular approach. Something that I work on actually goes in a little bit of a different direction. I work on a template-driven approach to identifying specific types of peculiar supernovae in your data sets. So in particular, I've been focusing on finding 91BGs in the SDSS photometric sample. 91BGs are different than the normal type 1a supernova population because they're both dimmer, they're redder, and the morphologies of their light curves are slightly different as well. So the way this works is you pick two models, one that represents the normal overall supernova population and another that represents the object that you're interested in. And then you run 4 template fits using these models. You take, using each model, you fit it in the rest frame blue band passes and you fit it in the rest frame red observations. And so this gives you an indication of which model performs best in the blue wavelengths and which model performs best in the red wavelengths. Next slide, please. When you put this information together, what you can do is now compare the chi-squared values in the blue and in the red. Objects that look more like a 91BG in both the blue and the red on the plot shown here are going to end up in the top right corner. These are the red points, which are spectroscopically confirmed 91BGs in CSP. The objects that look more like normal in both the blue and the red are going to end up in the bottom left. So these are the purple objects, which are again spectroscopically confirmed by CSP. This allows you to segregate out your 91BG-like objects, and then you can schedule them both for spectroscopic follow-up, particularly at late times, which is really important for constraining existing supernova models. And it also allows you to put stronger statistical constraints on population studies for things like host galaxy correlations. Thank you.
Okay, thanks, Daniel. And our last speaker will be Francisco.
Thank you. Hello, my name is Francisco Forster. I'm speaking on behalf of the ALeRCE broker, a Chilean-led broker which aims to provide a rapid and robust classification of variable events. Today I'm showing the first results of one of the 2 classifiers used by ALeRCE, the STAMP classifier. If you want to learn more about the Lightcurve classifier, see the parallel taught by Paula Sanchez-Saez in section H. So in this first slide, you can see the evolution of real Bose classifiers. Since the first work of Bailey et al. 2007, which used random forests and other more classical methods to separate real Bose in an automated fashion, in 2016, we introduced convolutional neural networks to this problem in Cabrera Vives et al. 2016. Now we also use a convolutional neural network, but we go beyond real Bose classification using an expanded taxonomy in Carrasco-Davis et al. 2020. This new classifier is able to classify ALeRCE into 5 classes using only the first STAMP triplet, with reasonable accuracy, as you can see in the confusion matrix on the right. And next slide, please. In order to take advantage of this classifier, we have developed a web interface called the Supernova Hunter. In this interface, users can explore the best candidates in real time, providing labels for possible supernova or Bose. Through this process, we have been able to significantly enlarge the sample of Bose candidates in our training set, obtaining more than 30,000 visual classifications. Next slide. Finally, I show some results allowed by this new classifier. On the top and bottom left panels, you can see 2 nearby supernovae which were detected by CDF and reported by ALeRCE using only 1 detection. After the first detection by CDF and a report by ALeRCE only a few hours later, a spectra could be taken significantly before the second CDF detection was obtained, many days later in these 2 cases. In the top and middle panel, we show some statistics. On the top middle panel, we show the cumulative distribution of times between report and first detection for both AMPEL and ALeRCE, without counting candidates twice. You can see that ALeRCE is dominated the 1-day timescale reports. On the bottom middle panel, we show the distribution of classified objects, which with almost 450 supernovae spectroscopically classified. Finally, to summarize, we have reported more than 3,000 supernovae to TNS, about 450 of them spectroscopically classified. ALeRCE is contributing most candidates on the 1-day timescale, which is critical for flash spectroscopy. And the price of doing this is about 20% contamination, but we expect that one-stamp classification will be very important for fast classification and follow-up under LSST observing strategy. And finally, if you want to see more details, see this publication, Carrasco Davis et al. 2020, which appeared today in the archive. Thank you.
Okay, thank you, Francisco, and thank you to all the speakers, especially for keeping within your time. So we'll move now to the question and answer period.
I don't, if you have a question, please put it on the Zoom chat or on the Slack channel. So since I don't see any questions for now, maybe I have a question for Francisco. So I just wonder, you only mentioned about supernova. So do you report other classifications to TNS?
Well, actually, we don't report the AGN classifications to TNS, nor the variable stars. We're first starting focusing on supernova.
Yeah, I'm just curious because there are different, transient like TDEs and others. Do you plan to expand your report to others?
Yes, we would like to do it. So TDS is an interesting case because they are classified as a AGN by the stamp classifier and as a transient by the Lightcurve classifier. So I think the combination of both will be important to detect these events.
Yeah, sure. Yeah, it would be nice to see more classifications there. So I have a question from for John. So I think it's from Rahul. So for John, you showed a noisy version of the sort to recover templates. Is that a function of the regularization parameters you use, and therefore can modulate the size of it?
Yeah, so for the regularization parameter we have, the higher value you have for that, the less noisy it is, but the higher bias you're gonna have in your reconstructed template. And so we chose an optimal value of that parameter by doing a 5-fold cross-validation to balance the bias and variance of the estimate. So we think that's currently with our current model, we think that's the best noise to accuracy ratio we're gonna get.
And I have another question.
For me.
I think it's for Francisco, right? Yeah. So yeah, it's from Robert Nikuta. So it was a bit quick and he didn't catch it. So is the Supernova Hunter interface interactive only, or is this also an algorithm that can be tied with an API? So Robert, please chime in if I didn't ask the question correctly.
No, I think it was perfect, Chien-Hsiu.
Yeah, so all our web interfaces use an API from in the back. So you can also query through an API. But of course, if you want to do this in real time, the best way is to connect to the stream that we use. But you have to be careful because one-stamp classification requires, at this moment, visual inspection.
Yeah, understood. Thank you.
And then have a follow-up question for John. It's from Rahul. So Rahul, maybe you can just unmute and ask a question.
Yes, I was wondering if you know what the size of this noise that you're getting because of the estimation is, and whether you've thought about studying the intrinsic dispersion in templates using this kind of a method.
So it's definitely interesting. I imagine that the how noisy your template is going to be related to, I guess, the broadness of different true spectra that are underlying the supernova in your sample. Like if they were all from the exact same template with no noise on it, I imagine it'd be a much less noisy reconstruction. I'd have to think about how, when you don't know what the true spectra underlying it are, how you would quantify just how noisy it is versus what are true features in the spectra. But that would definitely be interesting.
Okay, I have a question for Daniel, if there are no more in this talk right now. Daniel, I was wondering if you had tried using your method on any other types of peculiar supernova.
Ooh, good question. I haven't personally. This method is an extension of a method that was originally published in Gonzalez-Gaetano et al. 2014. And they did explore that question a little bit more, although not to its full completion. And it was shown that you can identify things like 1AXs, for example. Non-type 1A supernova, other than core collapses, which were treated as a contaminant, weren't considered. In theory, though, there should be nothing stopping you, so long as you have good representative models for your underlying objects.
Thanks, and I had a question for Alex too, as well, if I can go ahead. Alex, I was wondering if looking at all of this data on galaxies had given you any insights into the host mass bias.
That's a great question. So we ended up cross-correlating the GHOST database with as many host masses as we could get from other databases that we found. We found comparable biases to those that were already in literature, and in the future, we hope to derive the masses ourselves for these host galaxies in order to potentially develop a more robust bias.
Alex, if I can ask another question. So I just wonder, sometimes there are foreground or background galaxy which just coincide on the line of sight very close to the host galaxy. So is there a way you can disentangle those from your algorithm?
Also a good question. So in a lot of the database, after we made the preliminary associations with both DLR and with gradient ascent, we followed up with redshift information if it was available.
Yeah, that's a very clever way to do that. I have another question to John. It's from Francisco. So John, could you produce a generative model which produce a family of spectra instead of a fixed template or class?
So I think you mean like produce like a set of representative spectra for a class instead of just a single one for that class. Let me know if that's not what you mean.
Yeah, or some decomposition.
Sorry, say that one more time.
Or some kind of decomposition that you can use to generate continuous distribution.
Mm-hmm. So we've discussed that a little bit, and we've been interested in trying to figure out how to formulate this question in terms of some kind of generative model or neural network architecture, and we haven't done that yet. But if you have any good ideas of how to do that, I'd love to hear it from you or anyone else that might be listening. But that's something we are interested in.
Thanks.
Yeah, John, along the same lines, I was wondering, I didn't catch whether you were just using the average salt model for your simulations, or if you're using a range of X1 and C values.
So for the that kind of toy example I showed for the supernovae, we used a SALT 1 model with a certain value of those parameters with some random Gaussian scatter on those values for each of the simulated photometry. But the plastic data has a wider variety of different SALT 2 parameters. So hopefully when we apply it to that set, we'll capture some of that diversity.
I have another question from Raul to Francisco. So Raul, maybe you can unmute and ask the question.
So when you're doing the real burgers with the taxonomy, I assume you are doing a retraining with that extra information. Does that actually improve the real burgers classification that you originally had?
Yes, I mean, we've been through a learning phase 1 year, and now we're so the production database that you can access has different versions of the real bogus classifier. But the new database that we are releasing, you can access for testing purposes now. You can see in our GitHub repositories. This one has been populated with the latest classifier. And in the future, every time we change the classifier, we will populate all the previous objects with a classifier version tag. So you can go to previous versions of the classifier if you want to check. So basically, we have completely redone the probabilities table of our database.
Okay, thanks.
I had a question for Francisco as well. With the contamination that you have for Supernova, was there a particular other type of class that was commonly confused with Supernova?
In the ones we report to TNS, we don't know because they usually don't have a subsequent detection, and then we don't know what was probably a bogus. So I think that the biggest problem now we have is confusion with bogus candidates because of the pixel size of CDF. So I think in the case of LSST, we think this will not be as bad because of the better resolution. So even for a person, it's difficult to separate between real and bogus sometimes. So the same happens for the neural network. But it's not a particular class. I mean, we have much more type 1A supernova in our training set because we use spectroscopically classified supernova. So there could be a bias towards this class.
Okay, any more questions for our speakers?
I don't see them on Zoom chat or on the Slack channel.
Okay, if not, I think then we can conclude here. So thank you everyone for attending the Supernova session. And I think with the new schedule, you'll have, with the 2 minutes that we have left in this session, you'll have a 17-minute break until the next session. Goodbye.
Bye, thank you.